So I'm just going to give a very quick rundown of what is actually an extraordinary complex topic, and I'll have to do this relatively quickly. But what I'll try to do is cover the bad bits first, and then end up with the positive bits. And I say that because the basic messages in terms of climate change are not great for this region of the world, and we need to, I think, recognise that, because when we're thinking about adapting or otherwise responding to climate change, in a sense, we need to know what's going on and what's coming down the track. We also need to know how to adapt, who needs to adapt, what to adapt to, and the sort of mechanisms and support that can help us on the way. And so I'm just sort of going to cover those relatively quickly today. So the first thing is our greenhouse gas emissions, which are the driver of climate change, continue to go up. This graph shows over 30 years carbon dioxide emissions from fossil fuels and cement manufacture, those sorts of things. It's only part of the picture of greenhouse gases, but you can see that that's going up. Last year it went up 0.6%, the year before it was 3.5%, and that will continue whilst we have our foot on the accelerator of economic growth. If we go to the next slide, we can see that the current coronavirus, this is a projection of emission reductions due to the coronavirus, reduced economic activity. It'll probably go down by about 5 to 7% this year. And the question, though, is what happens afterwards. So next slide. And we might go on a snapback process, or we might end up doing something quite different and go on a reframing or renewal process where we actually decide to do, rejig the way we do things. And we've already started to see this in, for example, the way people work. So not necessarily doing the commute, but working from home 2 or 3 days a week and saving those fossil fuels and those emissions in the process, but also having more time at home with the kids as well. So there are options, there are choices ahead of us here. At the moment, the debate in Australia isn't really grabbing hold of this opportunity, but in other countries it is. And we need to think about what's good for us in the future. And that's not just about climate change, but it's how we can use this opportunity to change many different things about our society. And so the problem with climate change, though, is at the moment we're going up in terms of our emissions. Solving climate change climate change isn't going to be solved if we just level out emissions at something like 40 billion tonnes a year, which is where our current emissions are. To sort of solve climate change, we've actually got to take that curve and take it down to zero. And we've got to do that in the next 3 decades or so to keep temperatures within 1.5 degrees. That's the lower of the 2 Paris Agreement goals. And that's going to be really difficult. And the challenge here is that for every tonne of those billions of tonnes of carbon dioxide, round about half of it gets absorbed, a quarter of it gets absorbed by the oceans, a quarter gets absorbed by the trees, soils and grass on our landscapes, which you're intimately involved with, and around about half of it accumulates in the atmosphere. And it'll sit there for a couple of 100 years or more. And that accumulates on the carbon dioxide that was there from the year before, and the year before that, and the year before that. So all of that leftover carbon dioxide just accumulates year after year after year. And that's why levelling off emissions isn't going to solve the problem. That's why we have to go to net zero. Really pleasing that the ACT government has actually got a plan to do that. So net zero by 2045, which is what the science says is needed, and a plan to actually take us there, including already going 100% renewables. The ACT, believe it or not, is actually one of the leading jurisdictions in the world, and it makes me proud to actually be a citizen of the ACT for that reason. Now, if we go to the next slide, just to put this in context, what it's already doing, those emissions, in terms of our atmosphere. So these are records from ice cores going back almost 1 million years. You can see the little ups and downs. They're glaciations, ice ages, and interglacials, the warm periods between the ice ages. The temperature difference between those going up and down is about 5 degrees. So the difference between the warm periods of Earth's history and the cold periods of Earth's history is about 5 degrees. That's what it takes to drop our sea levels 120 metres, to put a couple of kilometres of ice over North America and Europe, etc. Only 5 degrees. So it doesn't sound like much, but it makes a huge difference when it comes to the whole of the Earth, the global temperature. And so when people talk about 1 degrees or 1.4 or 3 degrees or 5 degrees, put it in context with what it takes to give us an ice age, but we're heading in the opposite direction, an anti-ice age in a sense. And we're already at 415 parts per million. And you can see the natural variability of carbon dioxide in the atmosphere is between 180 and 280 parts per million. So we're way outside the natural variability. And this is definitively due to human activity. The next slide. So given that we've actually known if we put carbon dioxide in the atmosphere, it'll warm the Earth. So it's the basic physics of radiation. When you put greenhouse gases in the atmosphere, they absorb some of the heat radiation, the long wave radiation that comes off the Earth, and they intercept that, and then they re-radiate that in all directions. And some of that comes back to the Earth, some keeps going out towards space. And so the more of these gases you put in the atmosphere, the more it's like a blanket in the atmosphere that keeps that heat in that otherwise would escape out to space. And we've known about that since the 1840s. It was first conceptualized in the 1840s, and it was first measured in the 1850s. And it was first modelled in the 1890s. So this science is not new. It has been around for a long, long time, 170 years plus. And there's an absolutely massive, mind-bogglingly massive amount of evidence to show that this hypothesis, this characterization of what's going on, is accurate. And so it's not just the fact that we've got the paleo evidence, we've got massive amounts of contemporary data, whether it's from measuring stations on the Earth or out in the space or biological responses, etc. There's just a huge amount of evidence that humans are causing these changes. Now, this graph just sort of picks that up in terms of temperature. So, given that understanding that greenhouse gases warm the Earth, given that we've been producing lots of greenhouse gases for a long time and they accumulate in the atmosphere, it's not surprising that we're seeing a warming Earth. This is a graph from the IPCC. What it does is it separates out the different causes or drivers of temperature variation across the globe. The blue line is the natural variation, or the best estimate of that. Essentially, you can see that's flatlining, not going particularly up or down, slight downwards trend, very, very slight. The little dips are caused by volcanic activity. So when you get a big volcano like Pinatubo, spouts up lots and lots of ash and sulfates into the atmosphere, and they reflect the sunlight and the Earth cools down. And you can easily measure that cooling down. And not only can you measure the temperature change, you can also measure the slowdown in the rate of sea level rise. It's that pervasive and that significant. It impacts quite radically. Just a single volcano can impact quite significantly in terms of global processes. The orange line is the best estimate of our influence, human influence on climate through greenhouse gases and through land use change, so clearing of trees in particular. And you can see that keeps on going up. The red line is the combination of the two, the natural plus the human, and you can see that corresponds very closely with the observed, which is the little wiggly line in the background. That's the observed global temperatures. And when we actually look at those temperatures, we actually note that temperature across the globe has actually already gone up. Compared with pre-industrial, it's 1.1 degrees Celsius. So this number 1 degree was because it wasn't fully pre-industrial. But across the land surface of the Earth, because the land warms up faster than the ocean, we're actually already averaging 1.5 degrees above pre-industrial, and we're heading up a lot faster than that. So here in Australia, as I'll show you in a second, we're more than 1.5 degrees. And globally, including the oceans, we actually may get to 1.5 as soon as the end of this decade. And no one a few years ago would have actually projected that was going to happen. And if you remember, 1.5 is like a third of an ice age, and we're already there in terms of temperature change. And there's less than 1 in 100,000 chance that this isn't due to humans, so effectively zero chance that we're not causing this. So given that we're the cause, we can also be part of the solution, or we just need to understand that we're responsible and take responsibility for this. I'll show you one of the things that people don't talk about. People talk about global warming in a sense of talking about average change, but what this slide shows is that the averages are only a small part of the story. So what this shows is, again, global temperatures. So you see down the bottom of this, though, each of those little coloured dots down the bottom is a different temperature measurement station across the Earth. And they're aligned, so the black line, horizontal line, is the equator. The ones down from the equator are towards the South Pole. The ones on the top are towards the North Pole. So they're arrayed by latitude. And you can see they're colour-coded, so if in that particular year where this record starts, so it's an animation that goes through year by year up to the current times, you can see that in year 1900, there were some places which were about 2 degrees colder than their long-term average, the long-term average for that place, and there were some places that were about 2 degrees hotter than the long-term average for that place. So the temperature range in the year 1900 was roughly 4 degrees Celsius between the coldest place and the hottest place on Earth. And the curve at the top is simply the sum of all of those separate individual station records. So you can see in the year 1900, on average, it was 0 degrees, so it was pretty much on the climate mean, but there were some places that were hotter, some places that were colder. So if we kick that animation off, Matt, and you can see what changes over time. So this is year by year as we go through the record. And for me, this is one of the scariest things about climate change, because you can see that the average has moved up, so the peak of the curve on the top. But the really important thing here, particularly from a farming perspective, is what happens at the ends of the extremes. So you can see that coming up to the recent times, is there were places on Earth which are 5 or maybe even 6 degrees hotter than the long-term average. And there was also places that were 3 degrees colder than the long-term average. So that range, which was around about 4 degrees 100 years ago, is now doubled. So the risk associated with climate has effectively doubled. And as you probably know, is that it's managing the variability, managing the extremes, which is the big challenge. If we had a nice, even climate, it was the same every year, you'd be much more productive and be much less risky than it is. And this is really just a sign of how increasingly risky our climate is becoming. If we look at what's happening on Australia, so this is just the Bureau of Met's, you can download this yourself straight off the web. This is the New South Wales ACT temperatures, and you can see that last year we were almost 2 degrees above the Bureau's baseline, which is 1961 to 1990. So it's not a long-term baseline, it's a recent baseline. If you want to take it back to something like pre-industrial, add about 0.3 or 0.4 degrees to that. So against the pre-industrial, we're well over 2 degrees here in New South Wales ACT last year. And you can see that that trend, which is the black line through it, keeps on going up. There is no slowdown. In fact, if anything, there's an acceleration of temperatures. And last year was the hottest year on record with very hot daytime temperatures. We had the hottest summer on record, the hottest heat waves in several months, including in winter. We had the hottest day on record across Australia, which was peaked out at 41.9 degrees, averaged across the continent. And that was 2 record days. So the record was broken on one day, and it was broken again on the next day, and it was almost broken again the following day. It was only about 0.1, 0.2 degrees from breaking that third record on that third day. So this is really extraordinary. Things are changing, and they're changing incredibly quickly. If we go to the next slide, and again, when we actually look at the science, we actually see that there's high degrees of vulnerability, surprisingly high degrees of vulnerability to changes in temperature from some of our systems. In this case, this is what happens with wheat growing. This particular example, I think, is from Wagga, and it shows average yields with different temperatures across the growing season, or in the right-hand panel, it's across the growing season before flowering, before anthesis. And you can see that if you've got a cool year, you're getting something like 6 tonnes per hectare. You go up to a warmish year, like 21 degrees, and you've essentially shredded your yields. You're down to about half or 2/3 reduction. If you look at the period before anthesis, the more sensitive period, is that if it's a cool year, sort of averaging about 16 degrees during that period, you're approaching potential yield at 6 tonnes per hectare. It only takes a couple of degrees and you've halved your yield. It only takes 3 degrees and you've essentially removed your yield. So a few degrees averaged across seasons make big, big differences in terms of biology and in terms of productivity and profitability. There's a high degree of sensitivity to temperature, and a lot of people don't understand that degree of sensitivity. If we go to the next slide. And in terms of extremes, again, a Bureau of Met graph, what this shows is it's the area of New South Wales and EACT, which is experiencing what would have used to have been thought of as a very hot year. So it's what we call decile 10 years. So it's the 10% hottest year in the long-term record. And what you can see is that if you go back like 100 years, relatively small fractions of New South Wales ACT in most years would have actually been experiencing that very hot condition. But these days, almost 100% of New South Wales ACT is experiencing a very hot year. There is no place to go that you can escape. When you get to 100%, there is no refuge. You can't go to any place and escape this. It hits you everywhere. And the rate of change of that is, again, really surprising. That this is only at the start of climate change if we don't get our act together. And we're already experiencing what used to have been extremely hot years every year. And but the really important part of that, if we go to the next slide, is this isn't just on the hot extremes, but it's also on the cold extremes. So Steve Crimp's done his PhD on this, which looked at how climate change is actually driving increased frost risk. And we call it the frost paradox because whilst on average we're warming, the cold risk, the frost risk, is actually increasing for many of our industries. And this is associated with the synoptic pattern changes, which I'll show you in a minute. But what I have here is a little graph which sort of shows frost risk. This is again for Wagga. And what this does is it's a very brief summary of frost risk associated with last frosts. And what it shows on the bottom axis is screen temperature, so the temperature when you measure it in a thermometer in a proper climate screen. And so 2 degrees is a light frost, -2 is a heavy frost. So that's the sort of degree of frostiness on the bottom axis. And the vertical axis is day of year of your last frost. So day 180 is the middle of the year. Day 300 is around about now, sort of thing. And this is the frost risk map for 1950s, and then we'll go through these successively. So that's 1950s, next slide, 1960s, next one, 1970s, 1980s, 1990s, and the year 2000s. And you can see that even though on average we've been warming, the frost risk has increased very significantly in this part of the world. And it's not just this part of the world that this is happening. And so that's that idea of extremes. We're getting more hot risk to deal with and we're getting more cold risk to deal with. And that just makes farming that much more difficult. We moved to rainfall. So last year, the rainfall in Australia was the lowest on record. In fact, by quite a significant margin. This was particularly driven by what was going on in the Indian Ocean dipole. So we had a very strong positive Indian Ocean dipole event. And that's the gradient of temperature in the oceans to the northwest of Australia. In many places in Australia, it was the worst drought on record. We had towns and rivers running dry. We had the massive fish kills, etc. But in parts of Australia, you can see those blue parts of Australia, we also had record rainfall in some parts. And those two areas on the northwest and on the northeast are just associated with particular cyclones, which are strengthening in their nature. And that blue splodge on the right-hand side, the top, that was the event that killed about 500,000 beef cattle in Queensland. So these animals, they were coming out of a drought, they had very little feed on the ground. Along comes this rainfall event, which lasted several days, huge amount of rain, flooding. They couldn't get access to any food. They were cold because they were wet, and their energy balance just went negative and they died. And this was massive, absolutely massive. And again, this was just extraordinary. Nothing like this had happened in those regions before. So this is just part of that story of extremes. We're just getting those extremes hitting us harder and harder. If we go to the next slide, in terms of sort of rainfall seasonality, what we're seeing is the tropics move south. And in a sense, the inland desert move to the coast as things change. This is work from David Stevens in WA, and that's impacting on the distribution of production systems. So we're seeing things that used to be grown in northern New South Wales, down in southern New South Wales, like cotton, or even down in Victoria. And so these things are impacting on production systems right now. And if we go to the next slide, the thing that's driving these particular changes here in Australia is the synoptic systems, our high-pressure systems and low-pressure systems. And so what we've seen over a period of decades now is that the high-pressure systems are migrating further south. So typically in winter when I was a kid, those high-pressure systems would migrate around the top end of South Australia. Now they're typically migrating around Victoria or even Tasmania latitudes in winter. And that's pushing the rain-bearing systems, the cold fronts, further south. So it's raining in the Southern Ocean rather than raining in Southern Australia. And they're not only moving south, but they're also strengthening. And there's a really strong linkage here to climate change. There's an almost linear relationship between this and temperature increases across the globe. Now you might say, well, that's just a random chance. It's just we're just unlucky here in Australia. It just happens to be hitting us hard. If we go to the next slide, that's exactly the same graph, but looking from over the top of Antarctica down. You can see Australia on the top right-hand corner, South America on the bottom right-hand, and South Africa on the bottom left-hand. And you can see that pattern of movement of the high-pressure systems is global, or at least hemispherical in its nature. And those changes in high-pressure systems are not just driving the rainfall change, but they're also driving that frost change. So as those high-pressure systems migrate further south, they're actually bringing up, when they come along, they're bringing up subpolar winds, like winds from Macquarie Island latitudes up over southeastern Australia. So it's super cool air coming across the Southern Ocean, whereas in the past that would have circulated over the Great Australian Bight sort of latitudes. Much warmer oceans, much warmer air. And so these are things which are very distinctively linked to climate change. If we go to the next slide. So just to sort of put this in the context of what your operating environment is, what I've done here is just simply plot out, in this case for Southern Australia, the average temperature against the average rainfall for each year. So each dot is a year. So these are the years before 1950s. And you can see when you plot this out, there's a relationship between temperature and rainfall. So those years which are wetter, like this year, are also cooler. And those years which are drier are also hotter. And it's relatively straightforward, is that if you've got a wet year, you've got more cloud, that reflects more sunlight, and so you don't get the same amount of heat on your soil. But also, when you've got wet conditions, evaporation absorbs energy and it moves that energy off your land. And so without water on your landscape, you heat up the landscape simply because there isn't that what we call latent heat of evaporation being absorbed by the water when it evaporates. In a hot and dry environment, you don't get that latent heat. You actually warm up your land surface. We get really extreme temperatures like we did last year. So these things go together. They're not separate things, they go together. And I've just drawn around that essentially a hand-drawn ellipse, which is sort of the envelope of the operating environment. But you can see that that relationship is pretty strong, going from hotter and drier to colder and wetter. If we look at the next slide, which is going for the 1950s up to the end of last century and the years since year 2000, we can see that exactly the same graph, you can see that the slope of that line is exactly the same between those periods. So we get that strong relationship between hotter and drier and colder and wetter across those different periods. But if we go to the next slide, we see what happens if we overlay those on top of each other. We can see how different and how radically our climate has moved, our operating environment has changed. And so we can see that red ellipse, which is the most recent years, almost has no overlaps with what happened pre-1950s. And we can see that 2019, last year, was almost off the charts in terms of where it's sitting. And unfortunately, 2019 will become pretty much normal 2 decades from here. So that's the sort of change that we're looking. So rather than being an extreme year, it will actually become pretty much a normal year. It gets worse because what's happening globally is what we call the vapor pressure deficit, which is like relative humidity but flipped around, is actually increasing. So vapor pressure deficit is the difference between the amount of amount of water that air at a given temperature can hold versus what it does hold. So it's the deficit of moisture in the air. So it's a better measure than relative humidity for various reasons. But you can see that already that's going up across the globe and it's projected to go up further. Now, vapor pressure deficit is really important because if you've got high vapor pressure deficit, you get high evaporation from water courses, from your soil, etc. And also high VPD decreases your water use efficiency of your plants. Whether it's a crop or a grass, the higher the VPD, the less growth you get per unit water used. And so this is a really problematic picture as well. Now, not surprisingly, what we're seeing because of these trends across the globe is drought is increasing pretty much everywhere with a few exceptions, and Southeast Australia and Southwest Australia are parts of that global picture. We're not the only place to get increased drought. And if we go to the next slide, we can see that this is already impacting on Australia. Hit the next one. This is work from ABARES, where they tried to separate out the influence of better management and technologies compared with the climate signal. So when they look at just the climate signal, they're seeing a really significant reduction in productivity and profitability across Australia. So that improved management that you've all been part of has essentially masked the climate change signal, which is downwards. So in the absence of climate change, you would have probably gone up 22%. But because of climate change, you're essentially flatlining in terms of your profitability. And that's really large. If you look at the averages across Victoria, it's over a third. In contrast, if you go up to the northwest, where there's a long-term trend to increasing rainfall due to climate change, it's actually going up. So there's a really strong driver, and it's different from place to place. And the last slide, sort of looking backwards, is, if we go to the next one, is just what's happened to our fire seasons. And of course, we all know what happened in our last summer, and that was horrendous. And the various characteristics of changed fire risk don't tell a great story. So our fire season is extended effectively 4 months longer here in southeastern Australia. The fire intensity and frequency have increased. The area affected has increased, and that's indicated in that graph there. That graph is just for Victoria. And if you include New South Wales, it's much, much bigger. And also the days of fire danger have increased considerably. So we're actually getting a lot more fire danger days. And to put this in context is that going back decades now, when the fire danger index was developed, it was scaled from 0, no risk, to 100, the worst conceivable risk. The Canberra fires in 2003 were about 118 on that scale. The Black Saturday fires were 180 on that scale. So that's how radically fire risk has changed in a relatively short period of time. And again, no one was projecting this a few years ago. So if we move to the next slide. So just a couple of slides on what might happen in the future. And the really important thing in here is, unless we're careful, the future is simply an extrapolation of where we're coming from at the past. So it's just take those trends which we're experiencing and carry them out into the future. And that is not a great look for Australia. So this is a graph from the Global Carbon Project, which shows greenhouse gases against time. And it's just an extension of the same graph that I showed up first. So it's greenhouse gas emissions. But it's actually extrapolated also with different scenarios out into the future, out to the end of the century. And if we're not careful, we'll go onto this red curve, the top one here. And that will take us to a world which is 3, 4, 5, or maybe even 6 degrees warmer than our historical temperatures, with all of the implications that that has for agriculture and other activities. If everyone does what they said they'd do under the Paris Agreement, and most governments aren't, including the Australian government, then we end up with a world roughly 3 degrees warmer. But if we're actually to meet the Paris Agreement targets, which are well below 2 degrees and if possible 1.5 degrees, we need to go on those trajectories, the blue trajectory or the dotted line. And those are fundamentally different trajectories of emissions from where we're going. So some people look at that graph and they get very disturbed and think this is terrible news and we can't do that. And other people look at that graph and they say, wow, this is an opportunity. So if you're into renewables and battery storage and electric vehicles, etc., you say, well, this is my future. And so it's really important that the difference between this being good or bad is not existing in reality. It's merely in terms of how we receive the message and how we think we can respond. So that's in terms of emissions. It's not good or bad. I mean, it is bad in terms of agriculture, but in terms of emission reductions, it's about how we choose to position ourselves to deal with the future. And at the moment, with a few jurisdictions exceptions, such as California and the ACT, is that unfortunately we're heading up the graph, not down the graph. Now, what that will mean in terms of temperatures across the world, so this is top 2 panels is low emission scenario, bottom panel is high emission scenario, and then one in the middle. And you can see there's a big difference in terms of end of century temperatures depending on which pathway we go on. So we can go on a pathway which limits future temperature increases, or we can go on a pathway which just lets it rip. And if you look particularly, Australia's bad, but we're not the worst off in terms of temperature increases. If you look, say, up towards the Arctic, you see temperature increases of 8, 9, 10, 11 degrees. And you might think this is completely inconceivable and it's not going to happen. Well, unfortunately, actually already has happened. So a couple of years ago, the Svalbard seed vault which was there to store the seeds, wheat and sorghum and maize seeds, etc., forever in cold conditions, safe from any sort of harm, it flooded because the temperatures rose beyond what anyone projected, and there was no flood defences. And so that seed vault flooded, and that was like an end-of-century scenario, but it happened a couple of years ago. And so we need to be really, really careful about this. If we look at heat stress, which is the next slide, so this is projected to increase radically in this part of the world, but also elsewhere in Australia and globally. So this is some work I did about 20 years ago, but it simply looked at historical frequency of heat stress days. So a heat stress day is a day where humans or livestock can't get rid of the metabolic energy that we produce. So all of us produce about 60 watts of energy, and we need to get rid of that. Otherwise, it accumulates in our body and we die. So we sweat and we breathe out heat, etc. And so we all have mechanisms to get rid of our metabolic heat. But that becomes really difficult when it's really hot and humid, and that's a heat stress day, because those are conditions where you just simply can't easily get rid of your metabolic heat. And so if we look at the historical records, around about 70% of days were heat stress days up in the top end. Down in this part of the world, less than 10% of days are heat stress days. But under just a 2.7 degrees warming, which is pretty much where we're going if everyone complies with their current Paris Agreement commitments, you can see what the change is. So every day across the top end becomes a heat stress day. The sort of conditions currently experienced by Darwin are experienced across the top third of Australia. The conditions historically experienced by a place like Rockhampton will be experienced by a place like Canberra. And I've lived and worked in Queensland, in Rocky and Charleville and Gayndah and Townsville, and it's a fundamentally different climate than the one here. This is chalk and cheese. This is not at all similar. So these are radical changes in the working environment, in the farming environment that we'll experience. And the last couple of slides are on rainfall. So if we go next slide. This is the global rainfall projections for the end of the century with a high emission scenario. We can see that in the blue, in some places it's likely to get a lot wetter, but they're all already places which often have enough or too much rain. And in lots of places, including Australia, we're likely to get a lot drier. And these are typically places where we don't get enough rain, where we've got water-limited agriculture. So this is not, not a great look for Australia, but also for some of our competitors. You look at, various places in the world which are our competitors, and they're going to suffer the same sorts of things. So, of course, that means that's going to have, next slide, impacts in terms of our water availability. So this is a graph coming out of the last IPCC report, which showed changes in runoff. So runoff is what feeds our dams and our rivers, and per degree warming. So if you look at this part of the world, it sort of gives you an indication of around about 10% reduction per degree. So that means if we have a 3-degree scenario, that means we lose 30% from our rivers due to climate change. And again, you might think that that's high, but the Keynote report just a few months ago, in fact, indicated we're already there in terms of climate change reductions. And Southwest WA is particularly badly affected. And the really worrying thing is that these could well be underestimates. And if we go to the next slide, is that at the moment, with the exception of the Northwest, we tend to be tracking on the worst case scenario coming out of that report. And so for this area of the world, it's more like a 20% reduction per degree. And again, you might think this is radical, this is extreme, it's not going to happen. Unfortunately, it already has happened. So if you look over at Perth's dams, which used to get around 400 gigalitres of water per year on average, now get around about 40. It's a 90% reduction already due to climate change. So these dams, which were designed to store river water, are now storing desal water and groundwater, which is pumped for dry times. The function of these dams has fundamentally changed. And that's due to climate change. That's already happened. So that's like a 3-degree scenario for Southwest WA, but it's already happened right now, 2020. And if we look at drought, the next slide, again, regardless of which metric and regardless of which region in Australia you go to, is the projections for drought get worse and worse. So whether it's short-term droughts or long-term droughts, whether it's number of drought days, extremity of drought, is that it all gets worse. And so those are just little graphs. Sorry, they're very small numbers, but as you go to the right-hand side of each of those, you go towards the end of the century up to 2100. You can see the bars just get bigger and bigger as you go further and further out. And the last slide, if we go to the next, is just that variability story. So this year we're lucky, we've got a La Nina, it's wet and cool. We're thinking, and wouldn't this be nice if this was normal? But the challenge is, of course, that the flip side is the El Ninos, and they typically dry us out and make us a lot hotter. And the work here from the Bureau of Met, Scott Power, actually shows that we've probably already had a big increase in variability of climate due to El Nino. And depending on emission scenarios out into the future, that could go up a little or it could go up a lot if we go on a high emission scenario. And of course, variability is risk, and risk chews into profits and ability to make change. And so those sorts of changes are really worrying, and you can see the effect this year that El Nino, etc., has on us, or the ENSO system. And in a sense, whilst it's the good part of the spectrum, it does just reinforce that variability that we have in Australia, and that's likely to increase. If we go to the next slide, and actually I'll skip this one just in the interest of time, it's just risk diagrams. We go to the next one. And I just want to talk about adaptation. So this is the things we can do over and above reducing emissions. So the first thing I would say to do is we need to reduce emissions away from those high-end scenarios into very low-end scenarios. So, net zero by 2050 for Australia would be a good target to start to set, because it's in, there's more and more studies which show it's in the national interest to actually do that. The costs of not acting on climate change grossly exceed the costs of acting on climate change. And in many cases, there can be potentially great benefits from acting on climate change in terms of economic development, the Ross Garnaut book, for example. So the question on the adaptation front, which is, adapting to adjust to the changing climate, the question is, well, how do we adapt well? And there's farmers in the audience. Peter Holding, who's going to be talking soon, who's a climate variability champion from some years ago, recognised for his ability to manage climate risk in his farming system. And there's many of incredibly good farmers around Australia. In fact, probably if you're not a good manager of risk, you probably wouldn't be on the farm in the first place. But in terms of climate change, this is new stuff. This is not what we've always done. This actually requires new sort of types of activity to manage that. And what we find is that when we look at climate adaptation, it's incredibly contextual. So the idea of that fence line contrast that I've put up in the picture there is to demonstrate the effects that values have in terms of that contextuality of adaptation. So on the one hand, you've got a farmer who treats the land relatively gently. On the other hand, you've got someone who pushes their land pretty seriously. There's a different value set. There's a different appetite for risk with those two different farmers on one side of the fence versus the other. And that means they will want different adaptation strategies. The adaptation strategy for one will be different from the adaptation strategy to climate change from the other. And that can vary, as you can see, over the scale of centimetres. A handspan, one side of the fence to the other, and you've got a different solution. So there is no one size fits all. This is about targeting adaptations to fit the aspirations and needs and conditions that different farming enterprises have. And when we look at it, there's a huge diversity of options. So Chris Stokes and I put together a book on adapting Australian agriculture to climate change some years ago, and we listed out all of these adaptations that were available and considered at the time. And so some categorisations of them, you can do adaptations which are on-farm and you can do some which are off-farm, which includes diversification. It can be short-term or long-term. It can be incremental, so just adjusting your existing system, or it can be transformational, rejigging your whole operation, and I'll talk about that later. Or adaptation can happen at the institutional level, at regional level with land care groups and catchment management groups mediating more regional responses, or across the value chain. So if you've got working in part of a value chain, sometimes that adaptation has to happen at a value chain level. So all of these adaptations, in a sense, involve some degree of cost. You've got to do something new or learn something new or buy a new piece of gear. And all of them require some sort of change. You can't adapt if you don't change. That's the nature of the beast. And so the question, though, is how do we actually start to think about this? How do we measure up benefits and costs of adaptation? But one of the benefits that we've found of being adaptive and recognising climate change is that farmers who acknowledge that the climate is changing and are doing their best to manage that change turn out to be less stressed and more empowered than those who aren't. And so they actually tend to be in a better space in terms of mental health and a better space in terms of thinking about their future. And so they're thinking much more strategically. And so that is a really good news story. If you ignore this, put your head in the sand, you will feel mental pain as well as probably financial pain. So there's good arguments for taking this on board, in my view. When we go out and talk with farmers, we've done this, quite a bit. Probably with various people in the room. We find that there's lots and lots of adaptation options that arise for any given scenario. So there's no single sort of thing that pops up in all of the conversations. So I don't expect you to read this, but just as an illustration that if you've got different scenarios, lower rainfall, higher temperature, you'll get a set of adaptations. If you have more extreme events, you'll get a different set of adaptations. And of course, those might happen together, so you might need to combine the lists. But if we go to the next slide, is that what we find that we can work together as a research community with a farming community, and we can identify a whole range of things which make sense in different systems. So in this particular case, if you're into cropping, there's a whole series of things, some of which farmers are often already doing, such as reduced tillage and stubble retention, but they're an integral part of having a climate-adapted system in Australia. So if you're not doing these things, it's probably going to be costing you. So I won't go into the details of all of those things, but you can ask me questions later in terms of that. But there's a whole series of things which relate to changes in management or changes in support mechanism like decision support, precision agriculture, etc. So if we go to the next slide, and we can carry that through to the breeding program, so we can actually start to breed crops which are actually adapted to the future climate. So from the start to the finish, it can take up to 15 years to deliver seeds into the hands of farmers. And in 15 years, a lot of climate can change, as we've started to see. And so we need to be breeding not for the current climate, but for the future climate and for the future carbon dioxide environment, because carbon dioxide helps plants grow. So we need to take advantage of that. And at the moment, our breeding programs don't. And so we're missing out on a free ride because we're not being inclusive of those factors. And again, we don't want to go into those in any great detail, but it's just one example. We can actually breed for increased sugar storage in the stems of crops. And that actually is really important, because if you get into a dry period when you're filling your grain, the plant can mobilize that sugar, put it into the grain, even though you're getting a dry end to your crop. So there's lots and lots of things we can do. If we go to the next slide, we can do similar things for livestock. Now, this particular slide, I actually just went onto the Farmers for Climate Action website and actually just grabbed what they said about livestock adaptation and put it here, and then just cut a few words out. And I did that because it's really important to recognise there's a whole series of resources out there who can help you explore this adaptation space. And the Farmers for Climate Action is not only a great web resource, they're actually a great organisation to actually engage with, because in a sense they're the ones who are leading, both on the sort of political side, but also in terms of generating a community of practice amongst the farming community to deal with climate change. So if we go to the next slide, is that one of the things, though, we've found when we go out and work with farmers is that if we go out to a bunch of farmers and give them a climate scenario and say, how are you going to deal with it? The first response is all about agronomic change and incremental change. So it's, I'll change my planting times, you might try dry sowing, I'll change my cropping mix, etc. And so we can then go away and we can actually work out how much benefit that gives them under a particular climate change. We take it back to them and say, what do you think about this? Or are there other things you want to do? We do this several times. And what this shows in the different columns is just the results from the different years where we've gone and engaged with this same farmer group. And you can see that they started out with the agronomic and technical, but they finished with the strategic. And at the end of that process, they said the most important thing we can do is not the tactical, it's actually the strategic, it's the long term, it's how we position ourselves in terms of our business. And one of the other things, if you go to the next slide, is that we also have recognised, and various groups have worked with us, to actually understand how we can adapt to value chains. So if you have really good adaptation at a farm level, but your value chain hasn't adapted, it may not help you all that much. And vice versa. If your value chain's adapting, but there's no change at the farm level, there's big inefficiencies which can arise. And so we've worked with some of the big companies around Australia to understand their value chains and see how they can be adapted in a way which not only helps them, but helps the farming community as well. That just brings up the point that we need to think long-term, we need to think strategic. And that means that just focusing on tweaking our existing system, incremental change, may not be the best thing to do. It might be the best thing to do, but it may not be. And so I argue that when we come to significant revisions of how you're seeing your future, when you're doing some significant farm planning, broaden out the possibilities to not just include tweaking your existing system, but include what we call systemic change, bringing new elements into your system, or transformational change. So transformational change is where you fundamentally change the system or perhaps move your location. So an example would be where Brown Brothers moved some of their grape growing down to Tasmania. So they said this is getting too hot, too dry, too risky in Victoria, too difficult to get high quality grapes. And so they moved, bought up land down in Tassie. And that's not only provided them with an insurance policy for future change, it's actually delivering them benefit right now because they're actually producing high value, cool wines, cool climate wines, which sell for a premium price. And so this has worked really well for them because they thought transformationally, they thought about moving some of their system. Is that it's really important though, is that these sorts of transformational changes are not fundamentally about the technical and the sort of scientific side of things. It's much more about the psychological and social and economic aspects of the decision-making process. And this just illustrates this in the next slide. So this is work that I did with Anne-Marie Dowd some years ago, and we went out and looked at the social networks of people who were saying they're incremental adapters, so happy with what they're doing in spite of the change, and people who are transformational adapters, so people who said, we want to do something big, potentially risky. And those social networks are just essentially the big dot point in the middle is in this case the key person, and all of the separate little nodes with the lines are people that they know and talk about in terms of farming systems and climate change. And you can see that the incremental adapters had a really dense social support network or social network. And so they're talking lots of people, but they was also quite local. In contrast, the people who are doing transformational change had a much, much weaker social network, and that was often at a distance. So the farmer in New South Wales would be talking to a farmer in California, sort of thing. And so they had a very, very different social network. And that's really interesting because that paper on the bottom right-hand side, paper by Granovetter et al., which was produced a long time ago now, the title of that paper is The Strength of Weak Ties. And the hypothesis in that paper was sometimes weak social ties reduce the pressure of social norms and allow people to do much, much more adventurous change. So you haven't got people saying, "Oh, that's a really dumbass thing to do. Don't try that. We just don't think that's right. It doesn't fit with the way things we do around here." And so those sorts of normative pressures stop people from exploring new things. And I can tell you some horrendous stories about that stuff if you want. But if this is actually flagging that there's a really, really big difference between how people need to approach these different levels of change. In contrast, the information networks for these types of people were fundamentally different as well. So the information networks for the incremental adapters were very weak and very local. So it was, across the fence, across your farm or down the pub or in the supermarket sort of thing. And in contrast, the transformational adapters had incredibly rich information networks. They were absorbing information from everywhere because they knew that they were about to make a potentially complex, potentially risky, potentially large-scale decision, and they wanted the information that reduced the risk, etc., and made it more successful. So just to wrap up, is that, go to the next slide, is that it raises the sort of question for me about what is a good strategy for farming in a changing climate. And here I use my own version of what a strategy is. You can buy hundreds and hundreds of books on strategy from your local bookshop. There's whole shelves of stuff on this. But my version is essentially it's the game you want to play, or sometimes it's a game you don't want to play. That can be a strategic decision, and how you think you can win. So what is it that gives you a competitive advantage that allows you to make that strategy work, allows you to win that game? And so the questions are here in terms of climate change. What do you make your decisions on? The old climate or the new? Think back to those ellipses that I showed you, that fundamental change in our operating environment. How do you value your assets? And I would argue, a lot of farmers think the farm is their biggest asset. I would actually think that what's between your ears is your biggest asset. It's your experience, your ability to juggle many, many different things to come out with sensible, practical solutions. Are you still going to be thinking about farming for commodities, the canola in this picture? Or is it farming for energy, the old windmill versus the new windmills in this picture? Is it about farming for carbon, the trees on the top of the landscape? Or is it about farming for biodiversity? Again, the trees on the top of that landscape. These are all starting to be options, not necessarily as the main game, the main money earner, but as additional elements for an integrated strategy, additional elements which have other benefits in terms of climate change. So this is one of these strategic decisions. Peter Mailer, who's also Farmer Climate Action. This is a quote from Peter. He is, from I think a third or fourth generation farm up near the Queensland-New South Wales border. Solar farming is better money, safer money, easier money than farming, given the changes in climate that he's seen. And so he and his brothers have now got a thriving business in terms of putting solar out on farms. This is a transformational change. It's thinking, instead of I'm producing a commodity, now I'm no longer farming for wheat, I'm now farming for energy, I'm farming for electricity. This is a transformational change. And it doesn't mean you have to go all one or all the other, but it can be a lovely component of an effective farming system that gives you nice constant income streams rather than variable peaky income streams. So the last couple of slides is just about how we might think about this. So if we go to the next slide, Matt. So this is a diagram that comes from Peter Heyman and Uday Nidumolu from South Australia. And Peter talks about modelling the future, visiting the future, preparing for the future, and remembering the future. And just to explain these a little bit, so Matt, if you go to the next slide. So remembering the future is where you look backwards. You look backwards and you say, okay, well, we had a really bad drought in the 60s. How did we deal with that? Or how did my dad deal with that? Or mum deal with that? And so we learn from past experience. So we travel back in time to learn what to do now. That will become increasingly difficult as the climate changes, but it's still a viable strategy. We can do what we call visiting the future, which is thinking about climate analogues. So if you're in a place which is likely to become hotter and drier, you can go to a place which is now currently hotter and drier than you are, and find out how those farmers and that natural resource management was implemented in that place. And you can learn about what they do, how they do it, what dead ends they've gone down that didn't work, and bring that back to your own place here. And so you don't have to go down the same dead ends that they've gone down. You can actually learn from other people in other places. And that's, I think, a really powerful way of starting conversations and starting on this journey. We can model the future. So this is a sort of more scientific-y type thing where you can do climate trend analysis, the sorts of things I showed you before. You can do climate projections from global climate models, recognising that they're quite inadequate in representing some of the key things that are driving Australia's climate, like the high-pressure system migration. They just don't get. And putting that through a climate model, a crop model, like a yield profit type model. And you can understand, what might happen in terms of your systems and what you might do to adapt. And then lastly, you can prepare for the future. So you can say, well, the future is somewhat unknown, but we have some really good indications of direction. So in this part of the world, hotter, drier, more variable. And you can develop adaptation technologies and management systems that are suitable for those, and prepare so that you can actually splice them into your farming system when you need them. So it's doing your homework so it's ready when you need them, rather than having to wait some years to put them in place. And so it's building adaptive capacity, the knowledge that you generate from being in this meeting today. And it's thinking about systems of adoption and getting government to take this seriously and to support research and development into climate change adaptation, which has fallen off the cliff over the last years. Next slide, Matt. And in all of this, we need to think about emission reduction options. So when you're adapting to climate change, the last thing I would argue you want to do is increase your greenhouse gas emissions, because that just makes the climate change that you're responding to worse. So you go into a downward spiral. So another example would be air conditioning in a coal-fired electricity system. You're hot, you turn on the air conditioner, you produce more greenhouse gases, which raises the temperature, which makes you hotter. You turn on your air conditioner more. So these are sort of dumb things to do, and so we don't want to do those sorts of things. So when you actually look at the food system, it's a really big part of greenhouse emissions globally. So it's almost a third of greenhouse gas emissions globally. That's about the same number as electricity on a global scale. And most people think, it's a small thing, but it's actually a really big part of the whole picture. And so, in a sense, agriculture can't avoid being part of future emission reduction plans. So it's better to be proactive, in my view. And there's lots and lots of ways you can both adapt to climate change and reduce your emissions profiles. We've got some great examples in this region. John and Rob and I up near Yass are doing a great job of doing both of these things at the same time. And if we go to the next slide, is that in the IPCC, we pulled together all of the scientific literature which looked at synergies between different agendas. So those are the columns, like reducing greenhouse gas emissions, mitigation, adapting to climate change, reducing desertification, land degradation, and improving food security. So those are the agendas, the issues that we're trying to balance out. And we had, in this particular case, big groups of different management options that we could implement, such as improved livestock management, very broad category. The blue colours indicate synergies between those land management and those issues. And you can see that in every case, with the exception of food security and the bottom one, cropland conversion, there's a synergy. You can find options which allow you to adapt and reduce emissions at the same time. You can find options that allow you to adapt and improve food security at the same time. So there's a lot of good news stories. It's just about what you choose to do and how you choose to do it. And the example which is down the bottom right, which is that there's a trade-off between these couple of things. So it's because if you convert grassland to cropland, is that grassland produces less food per hectare than cropland does in terms of being able to feed people. And on a global scale, if we shift a lot of grassland to cropland, we improve food security. If we do it the other way, we decrease food security across the globe. So grassland has a lot more carbon in it than cropland typically, but it feeds less people. So just a quick summary, if you go to the next slide, Matt, is that climate is changing and is changing really significantly due to human activities. To our best of our ability to judge, is a lot more changes coming our way. And agriculture, which is already under stress, cost price squeezes, etc., is actually on the forefront, particularly in Australia and similar countries. And that's likely to push productivity down further, so it's likely to increase risk in terms of your management, and because of that increase in variability that I talked about and showed you. There's lots and lots of options to adapt to climate change. Not all of them will suit your particular circumstances, but some of them will. And so it's about finding out what works for you. And there's ways in which those can be implemented in most cases, which not only adapt to climate change and reduce risk, but also reduce greenhouse gas emissions from your farm at the same time and enhance livelihoods. So I think there's lots of good news if we choose to act in a sensible way. And lastly is that largely, particularly when you go to larger scale changes, the issues are not just technological. We tend to, government's technology roadmap, shovel some money towards the tech. That's actually not the big issue here mostly. It's about institutional change and social change and political change and cultural change. And we need to increase that nuancing of that discussion to move it away from just the tech. It's the tech plus everything else. And that's why it's really important to have a really effective policy framing to deal with climate change. The sorts of things we've got in the ACT, which is a comprehensive plan to deal with climate change, not a partial plan. And because if we do this well, we'll be better off. If we don't do it well, we will actually suffer the consequences, and that's what keeps me awake at night. Thank you.
Mark, thank you so much. And I think, chilling in so many ways. I was just reflecting, certainly in the 30 years that I've lived at Wallenbean, which is one of the absolutely most highly productive farming areas in southern New South Wales. We've seen a complete shift in the weather patterns when the rain comes, the timing of the breaks, and probably a 5-inch decline. We've got about 15 or 20 minutes now for questions. So if you'd like to ask a question, come up to one of the microphones and we'll go to you. Go ahead.
Thank you for that. Firstly, it was scary, but good. And this might seem a very obvious question. Why aren't politicians reacting urgently to this? And I'll just put just got 3 little sub points on that. So the gas-led recovery and technology seems at odds with your presentation. I've got Keith Hyde sitting next to me and he whispered raising dam walls. He's talking about Wangler Dam, no doubt. With 20% less runoff is just not bright. And we're talking about the appetite for variability of risk for farmers and our current government drought subsidies really rewards those who take on that high risk. So away you go.
That sounds like a Royal Commission, not a question.
That's not a bad idea, is it? That is not a bad idea.
There's lots in there, Vince. Clearly, there's people with vested interests and quite legitimate vested interests in the way things are. So if you've got a coal mine and threats to that coal mine and the possibility of that being a stranded asset are a legitimate concern. So we need to recognise those legitimate concerns, but that doesn't rationalise or justify national decision making, which prioritises and preferences those concerns versus other concerns and other opportunities which may arise from different policy settings. So in terms of you're talking about drought and drought subsidies. That's a perennial topic in Australia, and I do observe that many years ago there was a guy called Don Wilhite in the US who observed similar things in there than we do in Australia, and he coined this term the hydroillogical cycle, which was that we get a drought, people get concerned, government comes in pretty late. By the time they've done their assessments and started to get money, the drought's broken and people forget about it until the next drought comes along. And we don't actually make systemic changes either at the farm level or at the government level because we've got essentially a moral hazard that the governments will bail us out, so we don't need to change that sort of mentality. And so we haven't put in place I think effective, well, we did at one stage have a reasonably effective drought policy, but it was ditched going back a decade or so ago. And so I think we do need to reassess that and take into account climate change. So one of the big problems with the drought policy before is it didn't acknowledge climate change, just like the Murray-Darling Basin Plan doesn't have climate change in there. And when the changes we're seeing are so profound, it just leaves your policy stranded. And so, you've got, potential stranded coal mine type assets, we've got stranded policies, and potentially we have stranded ideas. So, for example, the whole idea of a gas-led transition between coal-fired to renewables is a stranded idea. It used to be part of the energy system lexicon going back to the 90s and perhaps the first decade of this century, but it's now not part of modern thinking about how we need to manage our electricity system going forward. It will be around for a while. We've got assets, various gas generators, etc., which are sitting there, but the rationale to build big new infrastructure like gas pipelines or a big new gas power plant in Newcastle is about zero. There's no one in the private industry who'll fund that because they just know it makes no sense.
I'd just add, while other people are perhaps approaching the microphones, that the other thing is not only policy settings, it's also finances. And many farmers would be aware of the scenario where you're carrying debt, but what the banks want to see is a very, very high input, high output system. And so you've got these scenarios where people might very well want to change their farming systems to do something more sustainable, but the banks would like to see $1 million worth of machinery, a huge investment in fertiliser and a massive turnover or a complete crash and burn. So farmers who are usually carrying debt are pretty trapped in that. It takes a lot of guts and a lot of support to be able to make those transitions. Yeah, go ahead.
Mark, thank you very much. I heard a theory on climate and the explanation. I was just wondering your opinion if it's sort of fairly close to it or way off. The idea that more energy is trapped in the biosphere by the greenhouse gases, so more energy then needs to be released by the climate, which is in the form of storms. Bigger winds, bigger tornadoes, bigger cyclones, bigger dry periods, bigger wet periods. Everything's more extreme because there's more energy in it. Is that a reasonable summation? Thank you.
Thanks for the question. So basically is that our weather systems are driven by heat from the sun, and weather is essentially the distribution of energy across the globe, and to distribute energy we distribute mass. So you get movement of water and movement of air in our weather systems, and so it's a pretty straightforward concept that if you actually increase the amount of energy, you've got to distribute that energy faster, and particularly during the transition period, if you go from this amount of energy to that amount of energy in your system, during that period where you're warming, you've got increased distribution as you shift energy around the Earth, because it's obviously hotter at the equator than it is at the poles, so you've got to shift that energy around, and particularly during that transition period, we get large-scale disturbances. So that's the things that we're seeing now. But there's other systems such as cyclones, which are simply just related to the temperature, the energy in your system. So if you've got a cool ocean, you don't get any tropical cyclones. It's only when you get a warm ocean you start to get the possibility of those, and the warmer the ocean, the stronger they get. And so some of these things are going to be transitional whilst we move from one state of climate to another, but others are just going to grow and grow and grow as we change our climate.
Hi, Martin Royds. I'm a regen farmer from Braidwood. Just wanting to question, one of your last statements was that cropping produces more food. And I'm just wondering whether it's food for us or food for the planet. Thinking back over the last 5,000 years, wherever we've cropped, we've left those land as a desert. And that's caused the climate change. And so maybe we should be questioning whether that is a true statement.
Yeah, well, I think it is pretty true both at the global scale and at the local scale. So if you've got just because it's cropland doesn't actually mean it has to be fundamentally unsustainable. But there's unsustainability built into any system which you take out nutrients and export nutrients from your system unless you've got some mechanism to replace those. And so if you look at, say, for example, Australia's wheat exports, we think about, millions of tons of wheat. Well, but there's also thousands and tons of nitrogen and phosphorus and sulfur which gets exported, and we're actually not replacing that. So any system which takes out more than it puts back in a sense, ultimately is unsustainable. And that's particularly important for Australia because we've got such poor soils. It's less so for Midwest US, for example. But the challenge here, I guess, is that we are dealing with human timeframes. There's the human frailty of short-term decision-making all the way through this. And we're not thinking about hundreds of years in terms of deep time. We are making decisions which are sometimes next week and sometimes next year, but even rarely next decade sort of thing. And so you're quite right to question the long-term sustainability, but in the short run, I think pretty much as long as you've got enough rainfall in the right environments to actually grow crops, you feed more people per hectare than if you had livestock. And that's simply when you're an animal like us or a cow eats feed, only a very small part of that gets put into productive use, milk or meat or wool. And whereas when you've actually got a wheat plant, 45% of it gets put into something which you can eat. And so
to a little bit, maybe we should be looking at how we crop, because there's pasture cropping techniques and things like that can be actually taking and building the soil at the same time and building biodiversity, rather than the technique that we've been using, which is a mining technique.
Well, I think that's a good
Thanks.
comment. And one of the really important things with pasture cropping, and as it's practiced by people like Cole Zeiss, is that it's just a low input system. So it's the opposite of what Genevieve was talking about. So by pushing down on your inputs, your productivity does go down a little bit, but your stability of your system increases, and again, depending on your time scale. But that idea of maximum yield does not equal maximum profitability is a really important one. And so if your bank's pushing you on one direction, push back.
Do we have any other questions from the floor? Yep, go ahead. We might make this the last one before morning tea.
Mark, it's good to be with you again and to hear an expansion of the thesis that you put to various land care groups around the country over the last couple of years. So thank you very much. Our land care groups have been dealing with water just recently because surrounding the ACT, Water New South Wales is reviewing all the basin plans and all the water strategies for the Murrumbidgee, the Lachlan. South Coast has just been advertised. Water is going to be a pretty scarce commodity in the next few years. Water yield from farms is not come into the debate at all, and neither have population pressures. All the pressures on Water New South Wales are coming from urban water supplies and irrigators, and everyone else is basically not being consulted with. So that's population pressures on one hand. Town councils want their towns to grow. They want more. They want more jobs. They want more rates, and that's the same with the ACT. Every expansion, population thresholds really need to come into this debate.
Yeah. Absolutely, and we have started some discussions with the ACT government about population scenarios building into things like climate change, and but it tends to be, particularly at the global level, population and population control is a no-go zone, and I think that needs to change. And we've seen a little bit of a thawing out of that over the last few years, but not comprehensive. The really important thing here is that we already have competition for scarce water, and what I've just shown you says that competition will just increase. And so for me, that just says we really need to get our act together in terms of having effective policies and mechanisms to deal with this issue in a way that is equitable, but also tends to promote stability in our system. So, the ups and downs that the rice industry suffered in the Millennium Drought is an example of not including the possibilities of change in terms of strategic planning. And so clearly it's in their interest to actually have stable water resources, but it may actually be not at the same level as if they get unstable water resources. And so starting to juggle up have systems which manage those different needs at different times, I think is really important. But one of the really critical things is water for inland towns. And at the moment, that just hasn't had the attention paid that it needs to. And so in various catchments that I read about, etc., is that you've got alternative uses such as mining, which actually happen at the expense of town water, and we really need to look after the towns.
Yeah, one very quick one.
Yep.
Great. Mark, it's been fascinating. I'm minded as we have this discussion that this is in some senses a self-selecting room full of people who care deeply about sustainability and those issues. As you were discussing the intense variability that we're seeing in the climate, I'm sure I'm right in remembering this, that on those 2 hottest days ever recorded in the ACT, we were also in the middle of summer gnats. So there's a whole other self-selecting group of people out there who chose on record-breaking days in the middle of the most extreme bushfire crisis we'd seen in 2 decades to pump out as many emissions as they could possibly manage. So I think it's fair to say that there's probably some distance to go in realising the impact on the community as a whole. But this has been fascinating, thought-provoking and yes, quite frightening. But please thank Professor Mark Howden very much indeed.